Welcome to Train Signal. I'm Ross Bagurtis, and in this video, other data link layer protocols and the physical layer, we're going to take a look at wrapping up all the technology and terminology we've talked about throughout the OSI model. So let's start with some of the rest of the data link layer protocols that are in our modern networks. So the data link layer protocols, some of these we've talked about so far. Ethernet. And Ethernet comes in multiple varieties. The IEEE, the Institute of Electrical and Electronic Engineers, 802.3 specification is for Ethernet. And that spec comes in different varieties. We have a 10 megabit spec, we have a 100 megabit spec, a gigabit spec, a 10 gigabit spec, and there's more specs to come that are used over both copper wiring and fiber optic cabling. Wireless Ethernet, we're most likely very familiar with. We've probably heard the letters and number combination 802.11a, B, G, N, or AC. AC is the brand new one that's just starting to gain popularity. Here, wireless Ethernet can operate at 11 megabits per second, 54 megabits per second, and even higher than that, especially once we get into the N and AC technologies, where we're actually using multiple radios in our wireless equipment to transfer information back and forth. So we have Ethernet, wireless Ethernet, both are controlled by IEEE. We have point-to-point protocol. So point-to-point protocol is used over serial links. We call it PPP. If you're old enough and you remember using maybe connecting to a bulletin board service in the 80s, possibly an internet service in the 90s, you remember using a modem, and those modems were pretty darn slow. As a matter of fact, it wasn't until the mid-90s where we got up to the 56 kilobits per second speed over a modem. Well, why am I talking about modems here when I'm talking about PPP? Well, when we used a dial-up modem, we actually used PPP as the data link layer protocol to send traffic over that modem. In that same way, we build bigger network connections using serial connections that are called T1s and T3s. Now, those T1s and T3s have a pretty ancient history. They were actually developed, surprisingly, in the 50s as the first mechanism to transfer telephone calls across the country without losing information. To give you a little sidestep on that, back in the 50s, when you made a long distance phone call from New York to San Francisco, the quality of the connection was so poor, you may barely be able to understand the person at the other end of the connection. They figured out how to convert the analog signal of the phone communication into a digital signal so that they can send that over long distances. And the difference there is that digital signals are much easier to clean up and repeat than an analog signal is. In the 50s, actually, we built this T1 technology to transfer telephone calls over long distances. And then in the 70s, 80s, and 90s, we began then to use those T1, T3 technologies to connect data networks together across long distances. At least in a production environment, we use those connections for our network connections. So we actually kind of bastardized this telephone technology to use it as a data network technology. The big reason we did it was that the wires were already in the ground. We just had to put a different endpoint on it to make it transfer data instead of telephone information, phone calls. So point-to-point protocol is responsible for all of this up at the data link layer. So the data link layer is going to use PPP to transfer information over T1, T3, and whatnot. And there's a variety of speeds for the serial links, all the way down to 600 baud, which is 600 bits per second, and all the way up 44 megabits per second and higher. The reality is that PPP links over serial connections are becoming much less common nowadays. We're moving much more to Ethernet as our primary mechanism to connect facilities together. Other technologies here. Asynchronous transfer mode. We use ATM over fiber optic cabling. Again, now we use ATM to transfer phone conversations over long distances over fiber optic cabling. So back in the 80s, the first fiber optic telephone network got installed across the country, and they needed a new technology to transfer those messages, so they use asynchronous transfer mode now to transfer voice calls over fiber optic cabling. It's much more efficient than the T1 because we can get a lot faster speeds over asynchronous transfer mode. We actually used ATM in data networking in the late 90s, early 2000s quite a bit. And that was until Ethernet became so popular and we kind of abandoned the layer 2 technology of ATM in data networking in favor of Ethernet. And the big reason there was that we have to support Ethernet for our end users. Ethernet's a very common technology, very easy and versatile. So we start to use Ethernet as our WAN links over fiber optic instead of ATM. So ATM is a bit antiquated as well. Data over Cable Interface Specification, DOCSIS, DOCSIS 3.0. This is a specific protocol to send data over a coax cable. So it's a mechanism so that we can have internet access over our cable TV line. You should be noticing repetition in what I'm saying here about how data networking evolved out of the telecommunications industry. So on the telephone side, we have telephone companies using T1s and T3s to transfer telephone calls cleanly and neatly, and then later on they adopted asynchronous transfer mode to do that. And guess what? The network engineers came along and said, ooh, we want to use that too because you have the wires in the ground. So they went and they kind of borrowed the technology because the infrastructure was already there. Network engineers didn't have to build a new infrastructure. Same thing with cable. In the 70s and 80s, we saw this huge cable TV infrastructure installed and maintained in order to deliver high quality cable TV service. Well, they wrote this specification then that just allowed the same cable to be used in order to send data network information over the cable TV network now. So we're repeating this again. And we're going to do it again here with DSL, Digital Subscriber Line. Here, we're going to use the infrastructure of the two wires that come into our house that run our telephones, and we're going to put different endpoints on the end of those two wires, so now we can send high-speed data network traffic across it. And I think now we're up to about 12 megabits per second over those two wires at a maximum. It's possible it's closer to 6 megabits per second, but either way, we get relatively fast speeds over these two wires that are coming into our house. So as we see technology evolve, we're going to see a repetition of reusing infrastructure over and over and over again. As a matter of fact, if you take a look at DSL again, this is kind of an interesting fact about DSL. Back in 1876 is when Bell came up with the idea and got a patent for a two-wire telephone. And guess how many wires your telephone has today if you have a landline installed in your house? 2. So we are literally using technology that's nearly 140 years old. We're using an infrastructure that has a 140-year lifespan. That is obscenely impressive when we're talking about data networking. We're using 140-year-old technology to actually transmit data at high speeds. Something that Alexander Graham Bell had absolutely no clue was possible when he developed this initially. Okay, let's talk about the physical layer now. So the physical layer is our wiring layer. It has specifications that are around it, but the specifications that are built around the physical layer are designed to indicate how the cable should be built. So we have Ethernet cabling over copper. And copper Ethernet cabling comes in category 5, 5E, and 6. It uses RJ45 cable ends. Over here in our picture, there are two kinds of category 5 cable here. There's UTP and STP. UTP is unshielded twisted pair. STP is shielded twisted pair. So these top three are unshielded, and the bottom one is shielded. And you know it's shielded because you can see this little aluminum or metal colored wrapper. I doubt it's aluminum, but it's a metal colored wrapper in there that's actually helping protect that wire from receiving crosstalk and other interference. The top three cables here are UTP, unshielded twisted pair, and they lack that metal shield around the wires. The idea behind the shielding is to reduce or eliminate two types of interference. And in the land of networking, we call them two types of interference, but in the world of physics, it's actually just one. So the idea here is that we have radio frequency interference, RFI, and electromagnetic interference, EMI. And the distinction is that RFI is usually from a known source, like a radio transmitter, cell phone, wireless access point, and EMI, electromagnetic interference, comes from things like fluorescent lights that have big transformers in them that create lots of interference. So in either case, if we run a Cat5, 5E, or 6 cable near a radio transmitter or across fluorescent lighting in the ceiling or across or near other highly electromagnetic devices, electrical devices, what's going to happen is that electromagnetic interference that's spewing off from those devices is actually going to corrupt the data that's traveling across our wire. So what we do to resolve that is one of a couple things. We either don't run those Ethernet cables across fluorescent lights and avoid any kind of radio transmitters, or we use shielded twisted pair cable. Serial cables. Serial cables, there are tons of different kinds of serial cables. V.35 is one, DS1 is another. They use a variety of different types of ends. Here we have a smart jack end at one, and this big giant plug at the other end. This big giant plug is a very old school plug. This little smart jack is a newer one. The DS1 cable accomplishes the same thing as this V.35 cable. It just uses RJ45 ends on it, and it uses Cat5 cabling. The difference is that we don't wire the ends of the RJ45 on a DS1 cable the same way as we would do for a Ethernet cable using Cat5. So serial cables are used in serial communication to hook up from our device to the telephone company's equipment. Fiber optic cabling now. And we usually use fiber optic cabling to transfer data over much larger distances. There are two types of fiber optic cabling here, single mode and multi-mode. We'll start with multi-mode on the bottom here. Multi-mode is a less expensive fiber optic cabling, and it is used to transfer network connections over shorter distances. Depending upon the speed you want, it can be anywhere from 550 meters if it's gigabit Ethernet, all the way up to a kilometer or so if it's a little bit slower Ethernet than gigabit. And the reason multi-mode is less expensive and can't travel as far is how the fiber is constructed. In multi-mode fiber, we use a pretty thick piece of glass. So if you don't know what fiber optic cabling is, the way they make it is they take a long cylinder of glass, maybe a couple feet long, 3 feet long maybe, and they put it under giant burners and they pull it. And they keep pulling it until the fiber optic cabling is so thin it's about the thickness of a piece of hair. So the multi-mode fiber is a little bit thicker than the single mode fiber. And what happens then is we use that fiber optic cabling and we fire a laser into the fiber optic cabling, and then the laser pulses, and the pulses of the laser indicate then the ones and zeros, the ons and offs, the bits of the data being transferred. So that pulsing light with the laser is then sent across the fiber optic cable at really fast speeds, nearly the speed of light, although light travels through glass much slower than light travels through air or than light travels through a vacuum. So, and this is going to become important later on because there are actually some technologies where we can actually get faster performance on a data network if we have a wireless network connection compared to a fiber optic connection, which is pretty impressive. At any rate, let's get back to multi-mode. So when we fire the laser into a multi-mode fiber, what happens is there's a lot of reflection inside of that fiber. So this laser light, when it goes in, it scatters all over the place. And because it's scattering and reflecting off the sides of the glass, we lose some energy during that process. there's a partial reflection of light process that's happening, and during that process, some of the photons get dropped, and the amount of energy traveling through that fiber optic cable drops. This is in contrast to single mode fiber. Single mode fiber has a much smaller diameter fiber optic cabling in the middle, and when we fire the laser through the single mode fiber, it does not bounce off the sides of the fiber optic cabling nearly as much. And because of this, we can get substantially further distances with single mode fiber as opposed to multi-mode. As a matter of fact, we can get up to 70 kilometers or more using single mode fiber and a specialized laser at each end. Now, before I had mentioned that we can get a faster data network over a wireless connection than we can over fiber. Well, this is true because the laws of physics say that light is refracted as it enters glass because light travels slower inside of glass than light travels when it's in the air, and it travels even faster in a vacuum. Well, why is this important in data networking? Well, there's this thing called day trading where you have stockbrokers and individuals in Chicago trying to do trading and taking advantage of inefficiencies in the market in New York. So these day traders actually go through extensive lengths to have the fastest connection between the two cities as possible. They have even gone to the lengths of reinstalling fiber optic cabling in a much straighter path to reduce the length of the cable in order to get the distance between New York and Chicago shorter. Because the shorter the distance, the less time the light takes to travel. Well, eventually these wireless nerds came along and said, oh, we can do a better job than that. And they found a way to implement wireless technology that can actually get traffic from Chicago to New York faster than over the fiber optic cabling. Now, they don't do this with two radio transmitters, or a radio transmitter and receiver in Chicago and New York. It's actually a bunch of point-to-point links that traverse radio towers through the entire span from Chicago to New York. So we're actually have network nerds that are helping out the business guys make more money by creating a faster data network. And they're doing it actually with wireless technology. Regardless, if I had to put my money somewhere and I wanted a stable, reliable, quality network, fiber optic is a really outstanding way to go. There have been some major initiatives in the last few years to install fiber optic cabling throughout the country. So as a business, there are a lot of businesses out there that do have relatively inexpensive access now to single mode fiber, so they can connect their facilities together at relatively low cost using Ethernet over fiber optic. Okay, so that's single mode and multi-mode fiber. Last, let's look at the connectors. I'm showing you 3 different fiber optic connectors here. There are a plethora of more fiber optic connectors. And hopefully the environment that you are in, if you do have to support fiber optic cabling, hopefully the environment that you're in standardized on something like the LC or SC connectors and didn't choose to use all 3. The organizations that I've worked for have not chosen to use all 3. They have just evolved into using all 3 different connectors. So the connector types here are ST connectors, and these are a little bayonet type clamp, something that you might see like on a CB radio antenna. The SC connectors are little square connectors. They're pretty fat. They're maybe half an inch wide. And then the LC connector is about a half an inch wide total. It's a very small connector. I always think of LC for little connector. It's very efficient, it's very nice, it's very neat and clean. The SC and ST can be challenging because they're a little bit bigger, they're a little bit harder to plug in and out because there's 2 ends to them. They're not locked together like the LC connector. Regardless, they're all fine, they're all effective. There isn't one that's better than the other. It just makes it problematic when you're trying to get a patch cable for your cable plant when you have to figure out what type of connectors you have at which areas of your organization. To give you an example of that, all of our switches used a GBIC, and the GBICs use an SC connector. Now, what the heck's a GBIC? A GBIC is an Ethernet laser for fiber. Okay, so the old school GBICs use these SC connectors. The modern lasers for fiber optic are called SFPs, small form pluggables. So depending upon the laser type you have is going to depend on the connection type you need. And then in the patch panel, so the patch panel is the place where all the fiber optic cabling for the building comes into, and then you just run a little patch cord from this main panel to the device that you want to connect to. And that patch panel may have one of these three types or all three types of connectors. At any rate, ST is the circle connector, SC is the large square connector, and LC is the tiny little connector. So this wraps up our conversation about fiber optic technology and other physical layer technologies, as well as the rest of the data link layer protocols that we use in data networking. Thank you very much, and I look forward to seeing you in future Train Signal videos.